All right, open up your book to section 7-5. We're on page 365 in your book. The title of this section is Parametric Functions. And our objective is, given equations of a parametric function, plot the graph and make conclusions about the geometric figure that results. If you go back and refresh your memory here a little bit, you'll hopefully remember that we've talked about parametric equations already. Back in chapter 1 when we were talking about inverse functions, one way to sketch an inverse function on your calculator is to use parametric mode, and that's because for parametric equations you have to write both an x equation and a y equation to define one graph. And that makes it really nice to be able to find the inverse then, because finding inverses just means you're swapping the x's and y's. So if I can come up with the original equation written as x equals something and y equals something, if I just take those two equations and swap them, I all of a sudden end up with the inverse. And so we used it for that purpose. We're going to use it for another purpose here in this section. Inverses is not the only reason why we use parametrics. This stuff that we're going to talk about in this section is not the only reason why we use parametrics. We'll study these even further later on. There are a lot of uses of parametric equations. All right, let's start out with a few terms here that we need to understand. The first one is the term parameter. Parameter is just a variable that we use, or the name that we give to that variable, that is now the independent variable in our equation. Usually we're using t for that. But now, instead of having y defined as a function of x, where x is the independent variable, instead I now have x defined as a dependent variable based on t, the independent variable. And y is a dependent variable based on the independent variable t as well. That's what we end up with when we're talking about a parametric equation, which actually I guess is jumping ahead here a little bit, but that's the next term here. Parametric equations are just two equations that express points x and y as a function of t, or actually as functions, it's plural, of t. So in this example you can see here we've got x is defined as some function f of t, and y is defined as some function g of t. Now it could be the case that those are both the same, but most of the time we're going to find they're different. But x is defined in terms of t and y is defined in terms of t. So we have to pick a value of t first, plug that into each equation to find a corresponding xy point, and then we can plot that point. And we repeat that process. Go on to the next value of t, plug it into both equations, come up with a new point for xy, and plot that point. And connect these with a nice smooth curve. The last term here for us is really the title of this section, which is Parametric Functions, and that's just a function specified by parametric equations. So a parametric function is just a function that's specified by parametric equations. All right, so let's take a look at a couple of examples here. Let's start with example 1 there on page 366. Example 1 is going to ask us to plot something in parametric mode, basically. It says to plot the graph of this parametric function in degree mode. They have x is equal to, I'll write this equation down, they've got x is equal to 5 cosine of t, and they've got y is equal to 7 sine of t. So there's our equation, right? Our parametric function that they want us to sketch. Now before you even sketch this, we're going to grab our calculator and do that in just a second, but before you even do that, think about what this equation is going to generate for me. Think about what is the domain going to be, what's the values of x's that are going to come out of this, and what are the range, what's the values of y that are going to come out of this. So if you look at the equation for x is written in terms of cosine. We know some things about cosine. Cosine is a function that oscillates between 1 and -1. The range of cosine is from -1 to 1, in other words. So if I multiply that by 5, if I take this inequality and multiply it by 5, I'll have -5 is less than or equal to 5 cosine of t, which is less than or equal to 5. And 5 cosine of t, that's x. So I know then that x must be between -5 and 5. Right there I figured out the range of this thing. I really don't know what the sketch might look like, but I do know that the domain of this. the domain is from -5 to 5. It's never going to give me an x value of 10 or 100 or -10, whatever. It's always going to be between -5 and +5. Likewise, we should be able to do the same thing for sine. The range of sine is the same as cosine, actually, so that's between -1 and 1. We're looking at 7 times that, so multiply through by 7. So I've got -7 is less than or equal to 7 sine of t, which is less than or equal to 7. And again, 7 sine of t here, that's y. So let's just replace that middle part here with y. And there we go. We've got that y is between -7 and 7. So I now have an idea on my sketch where this is going to show up. I do not know anything else about what the graph's going to look like, but I do know that it's going to be somewhere between my x's of -5 to 5 and my y's between -7 to 7. In fact, we can even think about perhaps what domain would make sense for t. Look at the t value that you're plugging in. You're plugging t into that trig function. In the x equation, you're plugging into cosine, and the y equation, you're plugging into sine. But I'm plugging into one of the two sinusoids, and I know the domain of, or I should say, I know that the period of those two functions is the same. In both those functions, the period is 2 pi radians, or in this case, they want us to do it in degrees, so I know that it's 360 degrees. So probably it would make sense from that information if I just consider t values from, say, 0 to 360 degrees. If I go past 360, that's just like wrapping back around to 0 and continuing on. Once I hit 360, it's the same thing that happened at 0. Cosine at 0 degrees is the same as cosine at 360, and at 720, and so forth. Same is true with sine. So if I want to sketch more of this, I could, but it's just going to start repeating itself is what I would expect, because these are periodic functions. Once I hit 360, these values just start spitting out the same numbers over and over again. Okay, so with that, before I even grab my calculator, I at least know what I'm going to plug in for my x and my y. I know what my t values are going to be, and I even know where to expect this to show up on my graph. Again, we said that from -5 to 5. Let's say that this is 5. I'll try to kind of measure that out there into -5. And in the vertical direction, we'll say that this is 7 up here, and we'll say that this is -7 down here. Right there is where this is going to graph. Whatever sketches, that's where it's going to show up. So let's see what we end up with as a sketch. So grab your calculator. All right, so with our calculator, go to your y, actually before we go to the y equals menu, we need to get ourselves in the right mode here. So hit your mode button, and let's go down to, first of all, putting this in degree mode, because that's what they said to do for this problem. And the second thing is where they asked us to sketch this in parametric mode, so switch over to parametric mode from function mode. All right, so now when you go to your y equals menu, let me clear out these equations I got there. In your y equals menu now, you've got an equation for x and an equation for y. So we are all set to type in 5 cosine of t for x1, and for y1 it's 7 sine of t. All right, so we got our equations put into x1 and y1 on our calculator. So now, if we go to our window, we need to set what our t values are going to be. And we also should set our corresponding x-min and x-max and so forth. So the t values, we just said that if we are going to graph this, it makes sense probably only sketch one period of these functions, because after that point it's going to start repeating. I'd suggest we pick the period from 0 to 360, but you could pick any interval that you wanted to, start at any point and end 360 degrees later. For your t-step, you want to pick your t-step to be small enough so that you get enough points to be plotted to get a good accurate sketch, but not so small that it takes forever to sketch this thing. So there's kind of a fine line here. But I think if we pick, say, a t-step of 4, I think that will be fine. 4 or 5 would be fine. If you take that interval from 360 minus the 0, the t interval that we're looking at, and divide it by this t-step that we've picked, divide by 4, that'll tell you how many points you're plotting here. So that'll be 90, actually 91 points that we're going to end up with in our sketch here. So that's a pretty decent sketch. And for our x's, I guess we did kind of narrow down what window makes sense there. Well, actually, let's keep it just in the standard window to start off with. And let's graph this. And here's what we end up with. Now, it almost looks circular here. Now, the reason why it looks circular is because of the fact that we don't have a square window. So even though we knew that this was going to show up from -5 to 5 and -7 to 7 for x's and y's, let's change our window here so it gives us a nice square window for this. So go to Zoom and choose option number 5 there is square. There we go. There's what this thing should actually look like. This is an ellipse is what we end up with. It's been stretched a little bit more in the y direction than the x direction. And again, count that out there. You can see that it crosses the x-axis there at -5 and 5, like we predicted, or it would have range from -5 to 5. And for the y's, it crosses the y-axis at -7 and 7. Let's grab a picture of that, and we will put it into our slide here. We'll go ahead and sketch it as well, but that tells us what this thing should look like here. So we can sketch our ellipse. Something about like this. It's a pretty decent sketch there of our ellipse. Okay. All right, look at example number 2. Example number 2 says for the parametric function x equals 5 cosine of t, y equals 7 sine of t. That's the one we just did in example 1. Eliminate the parameter, that's the t value they're talking about, to get a Cartesian equation relating x and y and describe the graph that you end up with. All right, so let's write down the equation again that they gave us. They gave us x is equal to 5 cosine of t and y is equal to 7 sine of t. That's our parametric equation that they've given us there. All right, to eliminate the parameter t, we're going to use one of our properties here that we've learned. And the property that we've learned deals with sine and cosine. It's a Pythagorean property. In fact, let's write this down. So the Pythagorean property, we know 3 of them actually, but the Pythagorean property that we want to look at is the one that's cosine squared. I'll put it in terms of t since that's what we've got here. Cosine squared of t plus the sine squared of t is equal to 1. And the reason I'm looking at this Pythagorean property is because when I look at my two parts of this equation here, I've got a cosine of t and a sine of t. And if I square those and add those up, notice what happens here. Here on this left side here, I've got t's in there, but over on the right side, they're gone. I'm eliminating that parameter t by using this property. So that's what we're going to do. Let's take these two equations here. And let's first solve them for the cosine of t and the sine of t. So when we do that, we'll have x divided by 5 is equal to the cosine of t. And we'll have y divided by 7 is equal to the sine of t. That's taking the two equations and dividing by the 5 and the 7 respectively there to solve for the trig function. And now if you take and square both sides of these equations, look at what we end up with. If I square the left side of this, I'll end up with, I'll just write it as x over 5 squared. And if I square the right side of this, I end up with cosine squared. And now to do the same thing here with the second equation. If I square y over 7, I get y over 7 squared. And on the right side, when I square sine, I end up with sine squared of t. And now what I can do is I can add these two equations together. If I take and add these equations together, notice what we end up with. On the left side, I'll have that x over 5 squared plus the y over 7 squared. And over on the right side, I'm going to have the cosine squared t plus the sine squared of t, which we just refreshed our memory there that cosine squared of t plus sine squared of t, that's our Pythagorean property, that's equal to 1. I can rewrite this as x over 5 squared plus y over 7 squared is equal to 1. That right there is the equation of an ellipse. We'll come back and study this more in when we get into the chapter on conics, but this is the equation of an ellipse. And it comes from the equation of a circle. You might recognize the equation of a circle. I'll put that over here on this side here. The equation of a circle is x squared plus y squared is equal to the radius r squared. That's your equation of a circle. If you want a circle with a radius of 1, then you can make r equal to 1. But if you take and, in fact, maybe I'll write it that way. Let me get rid of the r squared there. We'll just make it 1 with a radius of 1. If you take and divide your x's by some value, we know that's a dilation factor. You take your y's and you divide it by some value, that's a dilation factor vertically. So if you look at what we have over here, I've just taken my x's and I've dilated them by a factor of 5. I've only stretched them horizontally by a factor of 5. My y's, I did the same thing, but I did it by a factor of 7. So I've stretched further in the y direction than in the x direction. That's the reason we don't end up with a circle, but we end up with an ellipse, a circle that's been stretched a little further in one direction. All right, there we go. We've eliminated the parameter, which is really the tie-in to this chapter, by the way, is the reason why they're having us look at these parametric equations here is because sometimes we can use our properties from trig functions to help us eliminate that parameter and go from a parametric equation to a Cartesian equation in terms of just x and y. All right, let's take a look at one last example here. Example number 3. It says, this is on page 367 there. It says, the figure there shows the graph of a parametric equation x equals 6 plus 5 cosine of t and y equals negative 3 plus 7 sine of t. And describe the effect of the constants 6 and negative 3. Well, they gave us a picture here, but I'm going to think about this similar to what we did with that first example. So we have 6 plus 5 cosine of t, and we have y is equal to negative 3 plus 7 sine of t. Okay? So again, let's think about what exactly happens here with this cosine function, and when we multiply by 6 and then add the 5, what exactly happens there? So again, we can start with our with the same starting point here. I can say that negative 1 to 1 is the range of cosine. If I multiply by the 5 that I see there, I would have negative 5 is less than or equal to 5 cosine of t, which is less than or equal to 5. And now let's add on the 6. Add 6 to everything. 6 plus a negative 5 is going to be a positive 1. We'll have 6 plus 5 cosine of t. And adding 6 on to the 5 gives us 11. So it looks like now we've kind of shifted this interval over. Instead of being an interval between negative 5 and positive 5 like we started with, it's now from 1 to 11. So this looks like we're going to be just shifting this ellipse we sketched over to the right. Instead of crossing the x-axis at negative 5 and positive 5, where we're going to be crossing at 1 and 11, it looks like. Now, that's if we didn't also do a vertical, which is what the next part of this is. So again, start with the sine here. I know that sine has a range from negative 1 to 1. Multiply that through by 7, so this is going to be values between negative 7 for 7 sine of t and positive 7. And then add on the negative 3. Adding negative 3 to everything will give me a negative 10 is less than or equal to a negative 3 plus 7 sine of t, which is less than or equal to 4. So now instead of this oscillating between negative 7 and 7 like the original did, now we've shifted that down so it's from negative 10 to positive 4. So it looks like we've shifted this thing 6 units to the right, and that we've shifted this thing 3 units down. That's what these two guys here look like they're doing. Those look like translations that we've done. The 7 and the 5 were dilation factors, vertically and horizontally. The 6 and the negative 3 looks like they have the exact same results there, except they're translations. But now with this, I have an idea of where to start sketching this at. I think I do if I can look at my domains there. I got 1 to 11, and then negative 10 to 4. So you can sketch this over to the right. So if we say this is 1, we'll say that this is 11, and then 4 will be somewhere around here, we'll say. And negative 10, I guess is going to be way down here probably. Kind of roughly measure that out. That looks like about what we'd end up with. So it looks like I'd expect this thing to be that same ellipse, but it's going to cross here up at positive 4 and at negative 10. And it's going to oscillate between negative 1 and 11. It won't cross the x-axis there. But let's see what we end up with when we grab our calculator and sketch this. All right, so with our calculator, here is the original ellipse. Let's just modify that equation, actually. They told us to take 6 plus. Oh my goodness, maybe I'm not going to modify that. 6 plus 5 cosine of t. There we go. And then it was a negative 3 plus the 7 sine of t. There we go. And so we said that for a window here that would make sense. Again, we'll see the 1 full period of this from 0 to 360. For our x values, we said if we went from 1 to 11, that'd be fine, which actually this shows up there. And then for our y's, if we went from negative 10 to 4, that would show up. So actually, this will just barely fit on our screen here. So let's go ahead and sketch that, and there we go. Same ellipse, just been shifted over to the right and down is all that we see there. Let's grab a picture of that. We can sketch that in here. So again, we got some sort of an ellipse that does something about like this here. You can give yourself a little better sketch of that, but that gives us a decent sketch of what our ellipse would look like. Again, it's not crossing the x-axis at that 1 and 11. It's instead, that's how far it goes to the left and right. And again, it's going all the way up to 4, but all the way down to negative 10 there. So looks like those two values there are the translations, the 6 and the negative 3. In fact, that brings us to the general equation then for an ellipse, that if we're looking at the parametric equation for an ellipse, it's going to have this equation right here. X is going to be equal to h plus a times the cosine of t. Notice that the cosine goes with the equation for x. To help you remember that, think about the definition of cosine. Cosine is always the horizontal, the u value over r. The horizontal is an x value, so the cosine goes with x. Same is true with y. Y is associated with the vertical component. It's a y value, so it goes with y. But you have x is equal to h plus a cosine of t. And you have y is equal to k plus b sine of t. And the hk that we've got listed there is the center of your ellipse. We didn't actually mark those in our sketches. I guess we could have, but we didn't mark the center, but that's what the hk indicates. So the center of that last ellipse there was at 6, negative 3. And then the a value is what we call the x radius of this. It's the horizontal dilation factor, so it's our x radius. And the b is our y radius. It's our vertical dilation factor. If those two happen to be the same, then we end up with a circle. When they are different, then we got ourselves an ellipse. All right, that right there is the first half of section 7-5.